Andrea that will talk to you about alternative graph for the rescheduling of trains.
Thank you very much.
So you can start.
Many thanks.
Sorry, just one thing. We have 3 presentations.
Yes, I think so.
Yes. Oh, I said 2. Yeah, 3.
Yeah.
Okay. Again, thank you very much for the invitation. You can see here my name, Andrea D'Ariano. I work at Roma Tre University, Italy. Here you can find my contact information. I will talk about alternative graphs, yes, and I will tell you how these are applied to rescheduling trains. I especially work in the engineering department that has the stamp as an excellent department in Roma Tre University. This is given by the Minister of Education, both for high quality teaching and research. Some more information about myself. My background is in computer science, bachelor, master, and operations research. Then I performed a PhD in railway engineering and intelligent transportation systems. And now I am associate professor in operations research. Here you can see some achievements myself. Just mention the last item, that is the AIRO chapter on optimization in public transport and shared mobility. We actually do a lot of activities related to organizing sections, for example, to well-known conferences and research projects, interdisciplinary research projects. So if you want to know more about the chapter, just contact me or Valentina, that is the other coordinator. Here is just a picture about my research group. This was taken during the AIRO Young last year. It's an heterogeneous group. We have people from different countries in Europe. I mentioned our collaboration with France, UK, Netherlands, and so on. And also in China, we have a strong collaboration with different universities, top universities in transportation. For example, Beijing Jiantao University, Southwest Jiantao University, Tongji University in Shanghai. What is an alternative graph? Well, it's simply a way of formulating job shop scheduling problems. So I turn to the job shop scheduling problem. For people that do not know, job shop scheduling problem is a special case of scheduling problem. Here you can see a Gantt chart in which you see the time and you see the resources, and a job basically is a sequence of operations using the resources during the time. So you can imagine a job as a vehicle traversing a network, or a person using different resources of a network. It's important to state that the resources are shared, and you need to schedule, make a schedule of each resource, but also coordinate the schedule of different resources in an efficient way. There is a perfect matching between train scheduling and job shop scheduling. A job is indeed a train. A resource is a piece of track. An operation is a piece of track occupied by a train. So what we have to do is to have to choose a good routing of the train, such that you have a job for each train, and then perform scheduling decisions on each resource. More in detail, we use the alternative graph formulation of this problem, in which each operation is a node, and which each arc is a constraint. So it's a very simple way of representing a mathematical model. And we need to take into account special constraints. For example, the so-called blogging or no-store constraint that change a bit the nature of the job shop scheduling problem, make it more complex. So each resource can be occupied by at most one train at a time. So you see here, one train faces red, another one has a green, and then the green will pass first. You see the yellow, the violet color for the passing train. After the violet passes, then the blue can pass. So at the end, you have a conjunctive graph in which you basically simulate the traffic flows. But you have to decide the signaling, so the sequence between the two trains. Then there are many special constraints. Here, as you can see, I'm giving you an overview on the problem. high-level overview. Then I will be more technical in the second part. Special constraints can be related to the minimum start time of operations, and we can model it, for example, to a release time. That's the minimum time. And then regarding the maximum time, we have two ways of representing. One that is more soft, one that is more hard constraint. So soft constraint is something that you would like to achieve. I would like to arrive, I would like to process an operation at maximum a certain time. If I cannot, I can still delay. While if I have a deadline, the delay is no more accepted. Okay, so due date is more soft, deadline is hard constraint. Then there are many other types of constraints, for example, related to passenger services, connection between services, or related to rolling stock management, circulation. So different, the same rolling stock perform different services. And then you have constraints related to the timetable, arrival departure time, or related to the resource availability during time. If there are some works on some tracks, you need to take that into account. Or you can even handle constraints related to the travel time of train if you want to optimize the speed profile. So what are the modeling assumptions? More in general, we have that each operation has a start time, and the start time is basically a timing variable. And we assume that we know the duration of each operation. We just need to fix the start time. So it's a deterministic model. And then you have to decide the sequencing. The sequencing can be partially decided or totally free. In practice, you cannot decide the sequence completely flexible way, so we have some restrictions. Some trains must pass before others, but they have some flexibility. Where you have flexibility, optimization plays a role. And here you can see that, again, the blogging. So if I want to use the same track by two different trains, one should go first or the other. So either you select the alternative in which the red goes first, this arc, or you select the other alternative, the green goes first, this other arc. That's a sequencing decision. And then you have also routing. You can perform no routing. Sometimes you have no possibility to perform routing, or you might perform some local routing, just some minor changes in some stations, or you might perform a global routing, changing really the path of the train to different stations. Then you also might be flexible in managing the arrival departure times. If you are at the tactical level, you can still adjust the timetable somehow, while if you are doing operation, that's not possible anymore. And then you might deal also with the travel time adjustment between a certain time range, or dual time, that is the time given by passenger to enter, exit the train. And then all of this depends strongly on the level of granularity. How detailed should be your formulation? This has an impact on the timing decisions and then the composition of the networking resources. Overall, if you need to take a decision, you must face the most complex problem, that is the feasibility problem. Finding a feasible solution for this train scheduling problem in general, and also represented with this model, is an NPR problem. Just to give you an idea, I took a job shop scheduling representation in which I have to take a decision among these two dotted arcs. If you look at carefully this graph, you see that in terms of timing decisions, there is no feasible decision, because if you take this decision, you might end up in a cycle. So you cannot assign the start time of the operation in the cycle. And if you take the other decision, you end up in another cycle. So this just to tell you that that can be the case, that your solution is infeasible. The infeasibility might be due to decision taken during the optimization, or might be due to decision given by the decision maker. So you need to distinguish which is the region and give an answer, clear answer of what is generating infeasibility, and handle it. Assuming that everything is feasible, there are no infeasibilities, then if you want to optimize, the first thing that you optimize is timing decision. So this can be viewed as a makespan minimization problem, and use the well-known scheduling theory behind that. You can also handle other objective functions, but if you don't consider anymore the timing of the operations, but you consider more complex cost-related, for example, objectives, then you might lose the linearity and you might need more complex mathematical formulations and might be more difficult to converge. So the complexity of the problem also depends on the objective function measure, type of objective function you want to handle. Just so this slide about the literature showing that alternative graph approach is quite well used in rescheduling. As the most used alternative is a mixed integer linear programming formulation, but actually there is a strong interrelation between those two. Alternative graph can be viewed as a MILP, and a MILP can be used as an alternative graph. So basically, this is a kind of well-recognized approach. In general, there are other approaches. I like to divide in two mainstream. One is resource-dependent approaches, and the other one are time-dependent formulations. Of course, the alternative graph is more resource-dependent. There is not a best way of approaching it, this problem. Every approach has its own pro and contra. Okay, and mostly depend on the type of granularity for representation of resources and timing decisions. Okay, which type of solving methods you can approach with a general solver? This is easy to formulate. The contra is that the complexity is exploding in terms of computation time to find even a feasible solution when you have practical size instances. The alternative is what many practitioners are now investigating, smart solver, or if you want, problem-dedicated solver. So try to find a solver that makes use of the special characteristic of the problem. This allows you to have good performance and good scalability. The problem that you are facing in this case is that your approach might strongly depend on the business rules, the constraints you are considering, and the objectives. Changing rules or objectives might require a lot of work. The alternative graph is can be viewed as a way of representing the problem and solving in a smart way. And we developed for this a smart solver using heuristic, metaheuristic, and exact methods. That's the second part of my presentation. And what is in common of the two approaches is a kind of pre-processing phase, trying to filter the decisions that are obvious and try to avoid losing time on some decisions that can be taken, let's say, offline or based on the current state of the situation. This is very powerful when you deal with routing. Not all the routes are really interesting. You can filter the routes. There is a stream of research on that. And you can just use the most promising routes. Okay, what you want to solve a practical size problem, you need to decompose the problem. So you need to deal with having good performance, but also good convergence to feasible solution in a short time, especially for the rescheduling problem, and good scalability. So there are many different types of decompositions. I'll just give you an overview. First one is temporal based. So you can think about a rolling horizon or model predictive control approach, or you can use a spatial decomposition. A stream of research is on that. How to best coordinate the decisions in different areas. You can use, for example, benders, very efficient on that. Just mention Carlo Mannino, that is very expert on that, but also recently Francesco Corman developed some algorithms for just shop problem with benders. And then other types of decomposition are more based on the type of variables. So timing, sequencing, routing variables can be split, and the problem can be decomposed by different type of variables. Or you can decompose by layers, decomposing the problem in sub-problems and then find a way to solve them in a coordinated way. In this presentation, we will mostly look at the third type of decomposition, depending on the type of variables. Okay, now, second part of the presentation. As promised in the title, I will talk about rescheduling. That is one application of the alternative graph in the railway traffic domain. How to best reschedule trains when there are disturbances that cannot be absorbed by a robust timetable. You can design the best possible robust timetable, but real-time disturbances in general, might impact the feasibility of your timetable, and you might need to reschedule. So disturbance is, imagine a set of multiple delayed trains, a set of delayed trains, or some tracks that are blocked, or some other reasons. What we want to do is to define a smart, intelligent traffic management system that is able to achieve a good performance, for example, in terms of punctuality, or performance indicator anyway directly related to the punctuality, or if you want passenger satisfaction or improving passenger experience, or you can think about energy efficiency, so reducing the impact on the environment, or other objectives that similar concern. And then you have to reschedule trains. So this means resequencing, rerouting, taking new timing decisions. Okay. The railway engineering background is in this slide, very quick. I just tell you that you can use the block intent theory. That is a way to satisfy the minimum safety requirement between trains, both in space and time. And there are some special ways to be very precise on that. We take this into account when we model the problem, and the distance between two trains you can imagine as a block, the idea of a block. This block is occupied by the train that is in front. So it's not just the running time of the train, so what is related to the running time, but the block is larger for safety reasons, and consider a larger amount of space and time to have a feasible solution in practice. So this block it can be represented in this way with a time-space diagram. That's a typical way to represent it by railway engineers. And then if you look at one resource, for example, a piece of track between two signals, the blocks should not overlap. At most, they can touch each other, but cannot overlap. If the two blocks are overlapping, the solution is infeasible. So basically, you are detecting a conflict, and you need to solve a conflict. So the situation you see here is feasible. The blue train uses the top blocks, and the red one, the one below. What I want to do now is to show you a mapping between the railway engineering background and the optimization, and using the alternative graph. So, as I told you before, each node is an operation that starts at the beginning of a piece of track, and ends at the end of the piece of track. And then you have a new node, new operation. And then you have a fixed arc, that is in blue, that is used typically to model the travel time between two points in the network. This chain of arcs and nodes is a job. And then you have a certain weight, of course, of these arcs to represent the running time. The same applies for the red one. And then in between the two trains, we need to introduce the safety distance, safety constraints, but also we need to take the decision in general, no? Who goes first, which train enter first this junction. So if the blue one is first, we just need to insert one arc that is dotted in green for each resource and each pair of trains. And this is basically a solution. So this is a schedule. And then you need to give a weight. So this weight is set by taking into account the block, okay? The two blocks of two trains in one resource. In this way, you can get a feasible solution. Then you need to introduce additional constraint to represent the problem. For example, the expected entrance time of each train in the network. If you are optimizing this network, you need to take into account what's happening before and when the train is expected to enter. And you might, in this way, through the longest path from an initial fictitious node, that is the start of your optimization, to any node, for example, this one, you can simulate when is expected the entrance of the red train in this particular resource. So basically, when you have a solution, you have basically a simulation. When you don't have a solution, you need to schedule trains, the graph changes a bit and this becomes the alternative graph. Alternative means that you have two alternatives for each resource. Either you select the blue and then the red, so this arc, or you select the other one. The two arcs are paired, are one alternative or the other. So in this case, you have 1, 2, 3, 4, 5 alternatives. You have 5 sequencing decisions to consider. Then you might have additional constraints at certain intermediate nodes due, for example, to the scheduled departure time of trains in the timetable, or you might have some due date arcs to consider the objective function. For example, you want to minimize the delay at certain arrival time at certain point or passing time in certain point, exit of the network, and so on. And you might want to optimize objective functions related to time, for example, the makespan. And the makespan is used in this context to minimize the so-called maximum consecutive delay. That is the delay due to the decisions taken during this simulation. So this is basically the alternative graph. In terms of scheduling theory, this can be viewed as computing as a complete and consistent selection. Complete means for each pair of arcs, let's consider this as a pair, you need to select one arc for each pair. That's complete selection. Consistent means that there should be no positive length cycles in the graph, because a positive length cycle we have seen before is an infeasibility. So at the end, you will end up with a selection of green arcs such that you have a feasible solution like this. Okay. In this case, the red goes first and blue. Okay, so the problem can be viewed as shortest path computing, sorry, okay, better say longest path from node 0 to node n, minimize such longest path in the graph such that the solution is feasible, so complete and consistent. Okay, so now before going to the algorithmic part, you can first model it as a mathematical model, and as I promised to tell you before, as a MILP, fixed integer linear program. So it's a special linear program with some variables that are integer, other that are binary. The integer variables are related to the timing. So you give a name to each node, you give a name to the time of each node. So node 1 time 1. This is the start time of the first node. Then you give a name to each arc, so you can take into account the weight, and that is travel time, sometimes safety time. And then you can write the graph as a linear program, as you can see here. As I told you before, each arc is a constraint. So for example, if I consider this particular arc, this is the constraint here. T2 must be equal or larger than T1 plus the weight W12. So there is a perfect mapping between each arc and each constraint, and but still we need to take into account something, that is the sequencing decision. When you consider the sequencing decision, you need to consider the two green arcs, for example, these two green arcs. Each green arc you need to take into account with as a linear constraint, but the two have to be one or the other. To model the one or the other, we can use, for example, that's just a possibility to be simple in the explanation, a big M formulation, so that big M trick. The M is a very large number, and you use a binary variable. So if the binary variable is inserted in this way, is x is equal to 1, if one of the two constraints disappear, the big M, this constraint disappear. If x is equal to 1, you have the big M here. Otherwise, the other way around, if x is equal to 0, you have the big M on the other side. So every time in the model, at the end, when you select the variable x, you only have one constraint. We can visualize this in this way. If all the x are equal to 1, for example, this x is equal to 1, then you select this arc. And indeed, this is true, because you have that this constraint is always with minus m, so it's always valid, so it's totally useless. While this constraint must be satisfied. And this constraint states that T1 must be equal or larger than T8 plus the weight of the green arc. So the green arc is taken into account. Okay. Now you can model it and solve it with a software dedicated. What we propose here is a decomposition based by type of variables, and there was some 10 of years research on this, how to decompose and better solve the problem. I just give you a slide in which you have the type of decomposition. We first decided to attack the scheduling problem. So finding a feasible solution, fixing the routes, and then we relax the routing problem, and we try to improve some routes for some trains. So we develop a stream of algorithms on the scheduling problem, especially a branch and bound, an exact method, and then we'll develop a stream of algorithms on the routing problem. For those type of algorithms, we select more meta heuristics. First a local search and then some meta heuristics. Today we will see a tabu search. So let's have a new example just to better understand what we are doing. Here we have the formulation of the scheduling problem, in which a train route, a job is given to each train. So the route is fixed for each train. And then this is the problem to be solved. How can you solve this problem? For example, with a branch and bound method, how can be this branch and bound method? Each pair of alternative arcs is a decision level of your tree. So you can have a binary strategy. So you create two child, one in which you select the green before, for example, here, the green before the blue on the resource 8, or the other way around. And through this binary search tree, you can generate your branch and bound. As a lower bound method, we propose a generalization of this well-known Jackson-Prentice schedule, and then quickly on the branch and bound, we design implications rules to speed up the algorithm. So when you take a decision, you might have a consequence on other decisions, and so speed up your search. Or you need to design a searching strategy. For this problem, we design a hybrid searching strategy, depending either on the lower bound value or on the deepness in the search tree. With this method, you can compute a feasible solution, better an optimal solution, if you run the branch and bound completely. And this is imagining your optimal solution. So yeah, we selected for each alternative pair one arc. This solution is consistent. There are no positive elect cycles, and is optimal. And the optimal value is 8. The maximum delay is 8. If you look at the longest path, you will find that. How can we improve it through rerouting? Well, the red train can be rerouted. You can see here. So we can partially change the job of the red train, and we can try to improve the solution. Okay, so let's change the route with this new route, and let's solve again with the branch and bound. What you will see is that the sequencing, the optimal sequencing decision is different from before. Before the B was first and C. Now C is first and B. So as you see, even if you decompose the problem in type of variable, different types of variable, the different types of variables are strongly interconnected. So the problem is quite complex, both in scheduling and routing terms. How do we develop some intelligent routing algorithm? What we did is first we started with a local search. So let's start with the optimal scheduling decisions. So the graph representing the simulation with the optimal sequencing decisions. And let's take a routing move. What is a move? Changing the route of one train. How can I evaluate the route? Well, solving the new scheduling problem. How can I generate, so with this move, a neighbor? Consider a number of moves, changing, taking into account one train and changing one special route. So there can be many possible ways. What we did is developing a neighborhood, several neighborhoods, I mentioned just one, that is inspired on the critical path method. So let's look at the critical path. Which trains, so which jobs are involved in the critical path, which operations are involved in the critical path, and let's search for a route in which this operation disappears because you select another route. That's the idea. So we we found that this critical path method is quite good, but can be improved because typically, as you probably know, in the job shop, the critical path involves only a few trains, so a few jobs. So let's enlarge the concept. Let's ramify the critical path. Let me show you how we did that. So the critical path of the previous example is the gray one here. So the idea is, okay, let's change the route of train B and train C. Let's avoid that the train B uses some of these resources, 7, 8, 9, 10, and so on. But this is maybe not enough. Let's enlarge, ramify the critical path. Why? Because here the waiting operation that is generating delays. So the C is waiting for B because B is first. But this can be also disappearing if C is arriving sometime earlier or sometime later to the conflict point. That is the idea behind the ramification. So ramifying the critical path is changing the routes also before the point if there is a conflict, such that either the C arrives earlier and there is no more conflict respect to B, or C arrives sufficiently later and then there is again no more conflict. So this is the idea of ramification. This worked pretty well, and we ramified both backward and forward respect to the critical path. However, we discovered that this is not opto-connected. So you cannot, through a move in this way, ensure 100% that you are making a move toward the optimal solution. And this is very, very simple to demonstrate with our example, because basically to reduce the delay to 0, I didn't show you maybe before, a delay was 0. What we did is rescheduling the train A, but the train A is not involved in the ramified critical path. So our choice is not the best possible choice. So we need to perform also some other techniques. For example, you can to detect that the train A route is the most promising. So one possibility is, for example, implementing some restarts techniques and using some memory structure to avoid recycling on the same solutions. And this was the idea behind developing a taboo search algorithm. Okay, so a taboo search basically a large uses the local search and enlarge the scope of the search from local search to a global search, implementing some restart techniques. Now I show you some computational results. First, some results that are coming from a long time back from my PhD work, and then some other results that are being selected because these are connected to an industrial application. But it's also connected to the industrial application because my PhD actually was paid by Dutch infrastructure manager ProRay. So we performed in the Netherlands some tests. You see the gray area are the areas in which you can perform rerouting. The parts of the track in red were under construction at that point. We were thinking to investigate how to best use them. And then you have 40 trains per hour. Is a complex network because they have a lot of different types of constraints, for example, related to the rolling stock circulation, rolling stock connections. You have a lot of possible ways to reroute trains. The network is not so long, 50 kilometers long, and you have 40 trains per hour. Okay, the results were very promising because we started with the actual system, automatic route setting system in the Netherlands with no rerouting. They were not performing rerouting. Then we introduced intelligent routing techniques to the local search, and we improved of 50%. Then we introduced the branch and bound to sequence the trains with the default routes, and we improved much more. And then the best improvement was achieved with this experiment, halving the delay with a branch and bound and the local search. And all of this in a computation time that was compatible with the real-time operations, around half minute. And then we improved the results when we moved from the local search to the taboo search. Here there are different types of taboo search neighborhoods and strategies. As you can see in blue, the local search, a certain point is flat, is no more improving as you expect. No? While the metaheuristic is improving more, offer better solutions at the end of the computation time, that was 3 minutes, but also improves the solution in the first seconds of the computation, that for a real-time application is very useful. So we achieved that better solutions and also in a faster way. We perform a first set of experiments, on the perturbations, so delays. The second one on disruptions. We found that disruptions are more difficult to handle because there are less feasible solutions. So the rapidity to converge to good quality solution was slower because several times the methodistic was ending up in an infeasibility. So this was creating a little bit of problems on the finding a good solution in a short time. But still, the taboo search was much better than the local search. Now the industrial case study. The industrial case study, sorry, I'm a bit probably delayed. Okay, we'll be fast. We did a collaboration with Alstom Bologna, Alstom Italy, where they were developing a conflict detection and resolution system. They have this system that was working well, but not solving all the problems. Sometimes couldn't find a feasible solution. So they called us and asking, can you please replace our local solver with your alternative graph library of algorithms and finding a better solution? Okay, we try for that. The case study is the case study in the UK, starting from King Cross station in London. The complexity level is very high, very macroscopic level with the block signaling system, track circuit, very detailed representation of the network. And we thank Network Ray for this case study. And then we had to handle disruptions. That's why not feasible solution, because they have disruption. In this red box, trains cannot go with the original speed. They have to be either slowed down or they cannot enter the red area. So you can see in yellow several conflicts that have to be solved. And the other, you can solve them, for example, by postponing trains or by using the red area with the very slow trains. How can we best solve? How can we find a feasible solution and best solve? I just show you a couple of approaches. One is the mill formulation solved by Cplex. Another one is the alternative graph solver using branch and bound and taboo search. Actually, better results can be found through another methodistic that is variable neighbor search. But this is already enough to give you an idea of the potential. Cplex commercial solver, 1 hour time computation given. Alternative graph, only 20 seconds to be applicable real time. Cplex was failing 6 times on the 29 instances, while the alternative graph algorithms were never failing, so much more robust, let's say, approach. And the optimum was just 1 instance of difference, but Cplex was using more than 1,000 seconds of computation, so not applicable in real time, while alternative graph on average was using around 10 seconds, 11 seconds. So just one last, I skipped this because I'm going to take it too long time. Just one final slide in which I show you that we did this collaboration with the industry, and here you see how we show the results to the developers, to the railway managers, to the dispatchers. One of the computers in this lab was using alternative graph library algorithms, and we were solving on their traffic management system the conflicts and visualize the solutions. Thank you very much.
Thank you for your presentation. So same as this morning, if you have any question, don't hesitate to raise your hand or put the question directly in the chat. For the moment, I don't see anything in the chat, and I don't see raised hands. So I will start with one question from Dimitri, but since he lost his voice recently, I will give him mine. He's asking if when you have inconsistency with paired arcs, could you always have inconsistency with 2 arcs, or could you have inconsistency also with 3 arcs, and how do you deal with them?
Oh yes, you can have inconsistency with many arcs because it's a positive length cycle in the graph. So this can pass through many alternative arcs. Yeah, that's an interesting question. We need to investigate the nature of the infeasibility. There can be two options. One is due to the given sequencing decisions on the given constraints. In this case, you can demonstrate, you can prove that there is no feasible solution due to the entering constraints, given constraints. In the other case, that is more complex, is when the infeasibility is going to arcs in which you are deciding, the solver is deciding. In that case, potentially you should investigate all possible scheduling decisions to demonstrate that there is no feasible solution. So what we can surely do is the first case, solve the first case. We are very fast. While we have the second case, we need to run the branch and bound till you close all the trees. Sometimes we are not able to do that. In that case, if you have a truncated branch and bound, then at least you can tell the decision maker which are the trains involved in the feasibility and how you can broke the feasibility, recover the feasibility, without stating the best possible ways, but at least we recognize the problem.
I also have one question. In the branch and bound that you are using, you have some features like a branching rule, LD method. Do you think that these features could be included in Cplex? And do you think it would make it faster?
Oh yes, you can potentially use all the speedups in Cplex. For example, there are two types of very interesting speedup. One is related to the infrastructure that is offline. This infrastructure and the train routing characteristics. You can basically in this way filter the number of scheduling decisions. So you can do something like the preprocessing of Cplex outside Cplex. And the other one are the dynamic decisions. So sometimes we recognize that taking a decision for one train has a consequence on ordering the train A with first and train B, has consequences on other trains, and we have some dynamic implication rules that have been proved, and they can, of course, use for other solvers, other algorithms. I didn't have time to show you the details. Sorry for that. But these are very interesting. To be honest, the static implications are better because these can be always used because you compute them offline. The dynamic implications are tricky because sometimes they look like very promising, but if you use them, you need to investigate. You need to invest time on computing them, and sometimes the time that you invest on computing them doesn't pay back on the improvement. So it's really difficult. Sometimes instance dependent the improvement. So that's why we usually do some testing of the best configuration of the algorithms case dependent, distance dependent even. Yeah.
And Dimitri had a last question. He was asking if the optimal solution that you get with AGLIBRARY were found by Cplex or if they are different.
Yes, in the industrial case study, they were found by Cplex because for the rerouting problem, we only use meta-heuristics. Even if sometimes even with the meta-heuristic, you can demonstrate that the solution is optimal. For example, if the critical path gives a make span with zero delay, zero maximum delay, okay. Other cases where you were solved by Cplex with a very long computation time, we're using the lower bound of Cplex, yes. For the scheduling problem, we are able to most often quickly demonstrate ourselves, prove ourselves that is optimal. But for the routing problem, yes, we use Cplex.
Okay, thank you. I don't see any other questions. So thanks again for the nice presentation.
Thank you.
And I think we will move on to the next one.